Today I'd like to talk a little bit about how we represent nuclear processes and nuclear reactions, because in chemistry we usually think about things in terms of a chemical equation or a chemical reaction, and nuclear reactions are independent of the chemical environment. This is stuff that's happening because the particles of the nucleus are maneuvering and decaying in order to get to a more stable configuration. And there's various ways that they can do that. And I'm going to talk in the next series of videos, this one and a couple of others, on what these processes look like from a symbolic standpoint. So in order to talk about the nucleus, we use what are called nuclide symbols, which are usually introduced pretty early on in chemical classes. So in general chemistry classes or introductory chemistry classes, you usually at least see these nuclide symbols. So just as a reminder, if it has been a while, this number right here, this 92, if we look at uranium, which is U, on the periodic table, then uranium is down here at number 92. It's one of our actinides, so it's in those inner transition metals. And 92 indicates the number of protons. It's my atomic number, or Z. And that's a unique identifying characteristic for each atom. So that number is somewhat redundant, and sometimes with nuclide symbols, you just see the number at the top. And the number at the top is the mass number, or A. And the mass number is the total number of particles in the nucleus, the total number of nucleons, which means that it's the total number of protons and neutrons in that particular isotope of that particular element. So this would be read as uranium-238, and uranium-238, or U-238, is an isotope of uranium that is pretty common, that has 238 particles in the nucleus, 92 of which are protons and the rest are neutrons. And so that's kind of the information and the way that we can use that. You will sometimes also see them written like this, U-238. Which means the same thing. It's the same kind of notation, it's just a hyphen. The nuclide symbols, though, I think are a little bit easier when we're thinking about the reactions that are occurring. So the nuclide symbols in this format are going to be what you see in the next series of videos on these different decay processes. Okay, so the name of the game with nuclear chemistry is stability. We want to try to get to the most stable configurations possible. And so one way to do that is with alpha emission. Alpha emission is the emission of a helium nucleus. So if we think about helium on the periodic table, it's made up of 2 protons, it's number 2. And in a normal, everyday, run-of-the-mill atom of helium, it also has 2 neutrons in the nucleus. So 2 protons, 2 neutrons is what is emitted. The goal of alpha emission is to get smaller, right? I'm trying to get rid of those nucleons as quickly as possible, so I'm going to get rid of them 2 at a time and in equal amounts. So it doesn't matter that I have an imbalance. If you've learned a little about the region of stability or the band of stability, this is something that's up on the high end. I just have too many particles. And if we're thinking about those different conflicting forces there, strong nuclear force works under very short distances, small distances, whereas electric repulsive force is what splits everything apart. And the more protons we get in there, the more positively charged particles that we have in the nucleus, the more they're going to want to push apart and the less stable they are. So if we can get rid of some of them, then that's going to help. So the way that we represent alpha emission, let's use our 238 here. So here's my uranium-238. It's going to look very similar to a chemical process. So we still have an arrow that shows that this nucleus is going to go to something else. It's emitting a helium nucleus. So here's helium. I can write my helium nucleus in symbolically like a nuclide symbol, right? I have 2 protons, that's my atomic number, it is helium after all, and 4 total particles, 4 total particles of the nucleus. You can also see this sometimes as an alpha with 4, 2, so sometimes you will see the emission of an alpha particle that way. They both mean the same thing functionally. Now here's kind of the cool bit. because of the law of conservation of matter, which still holds in our universe, even with nuclear processes, then the total number of nucleons has to stay the same. So if I had 238 nucleons on this side, and I'm getting rid of 4 of them, then I have to have 234 in whatever is left over. And if I started with 92 of those 238 as being protons, but I get rid of 2 of them, then I have to have 90 protons at the end. Okay, now the cool thing about that is we know that the atomic number, that Z value, is unique to each individual element. So if I look at my periodic table and I go kind of 2 spaces down from my uranium, then I get to TH here, which is thorium. So what I've done essentially is I emitted this helium, this alpha particle, this helium nucleus, and then my uranium gets smaller. It changes into something else. That something else is thorium because I lost 2 protons. The identity of the element is going to be dependent on the number of protons that we have here. Okay, so let's look at another example of that. If we take another alpha emission, let's do radon, or let's do radium. We'll form radon. Spoiler alert. So radium is one of our alkaline earth metals. It's the bottom here of our alkaline earth metals, column 2 on the periodic table. So it's number 88. When radium emits an alpha particle, so here's my helium nucleus with the 4 nucleons and the 2 protons. Then what I have left over is 226 minus my 4 gives me 222. And then 88 minus 2 is my 86. So the numbers on the bottom have to balance, the numbers on the top have to balance. And when I look at the periodic table, if I move 2 back from my radium, 1, 2, that gets me to radon here in the noble gas column, which is actually pretty stable even though it is radioactive. It is after that 83 and up is all radioactive all the time. So it is still radioactive. It still is not stable, but it is a noble gas. And so it has the stability of noble gases and the inertness of noble gases, but it has the slight radioactivity to it. And radon-222 is in everything. That is the product that is all around us. It's in earth, water, air, rocks, everything around us. Because of its relationship to uranium, and it's actually a natural decay product of uranium, and it's one of the ways that we can kind of look at the decay process of uranium and the date of the Earth and various other types of features, various other types of bodies in the universe, right? So one of the ways that we use radioactive isotopes is in dating, and if I can figure out what their half-life is, then if I look at the decay process and how long this takes, and I know how many of these it's undergone, then I can determine how long the thing that I'm analyzing has been around, which is kind of cool. Okay, so that's alpha emission. The next is beta decay, or beta emission, which is kind of a wacky one, and it's all wacky. Spoiler alert, again, it's all wacky. Now, beta is either written as a beta, or sometimes it's a beta minus, and we'll talk about why we're making the distinction between a beta and a beta minus when we get to positron emission in a later video. So beta emission is when we have an unstable nucleus, because it's radioactive, and it's emitting a high energy electron. And this is from the nucleus. Now that should rankle you a little bit, because you look at that and you say, well, an electron from the nucleus, that goes against everything I've ever learned. Well, there aren't electrons in the nucleus, so what the heck is happening? Well, it really occurs because a neutron, which is a particle in the nucleus, is becoming a proton. And when it does this, it spits out an electron at a very high velocity. So if we think about this in terms of nuclide symbols, then we have a neutron, so 0 protons, 1 nucleon, is becoming a proton, which is 1 nucleon, 1 proton. And in order to balance this out, if I have a neutron becoming a proton, then I have to have 0 on the top. So whatever I have is not going to be a nucleon. And I have to have something that's adding to this to give me 0, so this has to be -1. Well, a -1 here is an electron. And that's the way that we'll see that there. So here's my neutron becoming a proton, and this electron here is my beta emission. Now you'll note then that while the number of protons in this reaction is going to increase by 1, the neutrons decrease by 1. So we're increasing the number of protons, decreasing the number of neutrons. And again, if you know something about the band of stability, then you can kind of see that if you're on one side or the other, then this is going to be an advantageous process in order to get you back into that stable realm. But you'll note that the mass number stays the same. So I'm not changing the number of nucleons, right? So the mass number stays the same, but I'm changing the composition of those nucleons. So let's look at this as an example here. Let's take carbon-14, which is used in carbon dating, which I was rambling on about just a second ago. So if we look at carbon-14 with its 6 protons and 14 nucleons, and it emits a beta particle, so I'm getting rid of my electron. In order to balance out this reaction then, my 14 stays the same, my mass number stays the same, my A value stays the same, and what plus -1 gives me 6? Well, that's 7. So if I look at the periodic table then, carbon is number 6, and what I functionally did was I increased the number of protons by decreasing the number of neutrons. So I bumped up to nitrogen. Kind of wacky. Okay. So let's look at another one. Let's take calcium. Calcium-47. Calcium is another one of our alkaline earth metals, so it's in the same column as radium. And when it emits a beta particle, or it undergoes beta decay or beta emission, then in order to balance this out, my mass number stays the same. And what plus -1 gives me 20? Well, that bumps me up on the periodic table to 21. So if I'm looking at what I am, what did I become? Here's my calcium, and I became scandium. All right, so we can start to predict then the products if we know what's being emitted in these reactions. So if I know that it's going to undergo alpha emission, or if I know it's undergoing beta decay, then I can figure out what the potential product is going to be by factoring that in using these nuclide symbols. So it's kind of a fun way. It still looks a little bit like chemical reactions, but in kind of bizarro world chemistry reactions. So we'll talk a little bit more about the other 4 types of radioactive decay in future videos. And as always, if you have any questions, don't hesitate to reach out.